Hello everyone and welcome back to this next lecture in the machine simulation series, and this is where we had left off last time, where we had examined how the rotor inductance of a salient pole induction motor is independent of the rotor position angle theta m, and we had done that using flux diagrams. So now coming back to the squirrel cage, or rather cylindrical motor, squirrel cage induction motor, we now have to examine this last one parameter in our equations, which is the mutual inductance between the stator and the rotor. For a cylindrical rotor, which is the case of a squirrel cage induction motor, we had found that all these other parameters were independent of the rotor position angle theta m, which means stator resistance, stator inductance, and rotor inductance were all independent of the rotor position angle. In the case of a salient pole induction motor, we found that the stator inductance is dependent on the rotor position angle, but the others were independent. Right? So now at this point, I'll stop the discussion on salient pole induction motors, because the main idea was to tell you about how we can use flux diagrams to interpret whether a parameter varies with respect to the rotor position angle. So now we come back to a squirrel cage induction motor and we look at this last parameter and we try to figure out if this is now dependent on the rotor position angle. So before I start this lecture, as always, a little bit of brief background, that if you're interested in these kind of video lectures but you want something a little more comprehensive, I do have full-length online courses which you can access on my own website, which is pythonpowerelectronics.com. So this website, pythonpowerelectronics.com, is the home page of this project, Python Power Electronics, and this is the home page, as you can see it. So this button, there are these 4 buttons. These are the 4 major buttons on this page. If you click on Learn, it will take you to the list of courses. So as of now, I have 5 courses. The very first course I have is Simulating Power Electronic Circuits Using Python, and in this I talk about the basics of how you can use Python and Python Power Electronics to simulate power electronic circuits. The second course I have is called Basics of Digital Signal Processing for Power Engineers, and in this I talk about how you can use Python and packages such as the signal package within SciPy to design and analyze filters for power engineering applications. The third course I have is called Simulation of Magnetics for Power Electronics Using Python, and in this I talk about how you can use Python and Python Power Electronics to simulate magnetic components such as inductors, coupled inductors, and transformers. The fourth course I have is called Control Analysis with Python for Grid Connected Converters, and in this I talk about how you can use Python and packages such as the Python control package to analyze and design controllers for power engineering applications, with the specific example of a single phase inverter connected to a single phase grid. And the very last course I have is called Why Specialize in Power Electronics, and in this I talk about why you should choose power electronics as a specialization by describing some of the challenges and opportunities available in this domain. So this course is a free course which is targeted towards junior undergraduate students or towards high school students who have not yet chosen their either engineering domains or their specializations within their engineering domains. So all these courses are available on 2 platforms, Decibels Lab and Udemy. If you click on any of these links or these buttons, it will take you to the link for the course. This link of this page is provided in the description of this video, so if you're interested, please do check out the description of this video. So with this, I'll get back to my lecture. So in these equations, as said before, our objective is to sort of quantify, or rather begin to understand, how the mutual inductance between the stator and the rotor is impacted by the rotor position angle. So we've seen already that the flux linkage of the stator and the flux linkage of the rotor can be expressed using this equation, where we say that it is the sum of the flux produced due to the self-inductance and the flux produced by the mutual inductance. So therefore, you could say that in a machine such as an induction motor, the flux that links with the stator is the flux that is produced by the stator as well as the flux produced by the rotor. So for example, let me go over to this diagram and explain using our usual thing here. So for example, we know already by our basic description that due to the currents flowing in the stator, this currents flowing in the stator will produce a magnetic flux. This magnetic flux will induce currents in the rotor, which will cause currents to flow in the rotor. Due to the current flowing in the rotor, which are these rotor bars short-circuited on either ends, the rotor also will produce a magnetic flux. So this stator flux is linked with the rotor, and similarly the flux produced by the rotor will also link back with the stator. So it's kind of an interactive system, right? Therefore, you could say that if I'm looking at the flux linkage of the stator, there are two fluxes in action. The flux produced by the stator itself, which is the self flux, and the flux produced by the rotor, which is linking with the stator, and this is the mutual flux. So before we actually go into this, let's talk about here how we described here how we would talk about a mutual flux. So in general, when we talk about a mutual flux, let us say we have two coils. So I'll say coil 1 and coil 2. Now we already know that coil 1 and coil 2 have self-inductances L1 and L2, and these self-inductances can be defined in this manner. So if we assume only one coil to be energized, in that case, if a current flows through one of the coils, then it'll produce an ampere turns, which in turn will produce a flux, and this flux will produce a flux linkage when we consider that if we take that the number of turns of these two coils are N1 and N2, right? So we can just use this formula. But now we are saying we want a mutual flux. So mutual flux means that if we energize coil 1, so energized, but flux linkage, that is I say psi 2. So this is psi 2 is the flux linkage of coil 2 is to be calculated. Then in that case, we say that this is due to the mutual flux because coil 2 is not energized. So any flux that is linking coil 2 is due to the mutual flux from coil 1. So here again, we can of course use more or less the same procedure. So let's say for example, we say that a current I1 is flowing through the coil 1. So therefore this is ampere turns of coil 1. AT is merely an acronym for that. So if I say that there is a current I1 flowing through coil 1 which has N1 turns, then N1 into I1 is the ampere turns of coil 1. Similarly, just like we did for the case of this induction motor, we can say that there is whatever flux path we choose, we can calculate the reluctance of the flux path, and we've done it in the previous lectures where we've calculated, or rather we said that we can map out flux paths, and flux paths can be divided into different parts and each part has its own reluctance. So in the same way, we can say that let us take N1 I1 as the ampere turns and divide it by the reluctance of the flux path, and this of course will give us a flux. So we can say this is flux 1 which is produced due to the coil 1. Now this flux 1 produced due to coil 1 is linking with coil 2. It will also link with coil 1 to produce a self-inductance, but we are no longer interested in that because we've talked about this before. We are now talking about mutual inductance. So if I say psi 2, which is the flux linkage of coil 2, this flux linkage of coil 2 will be flux 1 multiplied by N2, which is the number of turns of coil 2, right? And if I say that this psi 2 is so much, in that case the mutual inductance is equal to psi 2 divided by the current I1. And once again we can say exactly the same thing as before. So we can say that mutual inductance, that is mutual inductance will be 1 Henry when a 1 ampere current flowing through a coil produces a flux linkage of 1 Weber per turn in the other associated coil, right? This is what we're going to do. Now we are going to repeat the same process that we did with our flux diagrams for self-inductance, but this time we are going to look at mutual inductance. And for mutual inductance, we are going to use the same process, that is we are going to use at flux diagrams. So let's go over to our Inkscape, which is where I was using for drawing, and let me create a new file because we need something new to map out of mutual inductances. And I'm going to copy this entire diagram and paste it here and bring it down. So we now have created a copy of our flux diagram in a new one, and the reason I'm doing this is because we would like to now use this for mutual inductance with both of them. That way, in one case we are going to consider the stator to be energized, and in the other case we're going to consider the rotor to be energized. So this is what we will do now in this new file. So in this diagram we can use this same diagram, but we're going to try to use a slightly different approach in trying to figure out the mutual inductance. For that, first thing we need to do is we need to come up with an effective flux vector. So the first thing is, let's consider these two, the way we've represented our flux, our stator. So we have represented a simplified stator winding where we say there are only two stator slots diametrically opposite each other in the stator, and the entire stator coil is wound along these stator slots. So we also assumed that in any one of them the current has to enter the page, and in the other the current has to leave the page, because after all it's a coil carrying a current. So now if I assume that this conductor here, this slot here has conductors where the current is entering the page, then by using the right hand thumb rule we can conclude that these flux lines will be in such a direction that they'll be in the clockwise direction, and therefore in this slot, these flux diagrams produced by the conductors in this slot will be in the counterclockwise direction. And you can verify them yourself. You can even choose another direction and reverse these flux diagrams. It's not a problem. Discussion remains more or less the same. The concept is the same, right? So let us say that we have these flux diagrams, right? We can draw a few more flux diagrams as well, right? So if I say that these flux diagrams are continuously extending. So these flux diagrams are continuously extending and using the same path, and the same can be said here as well. So you could say that all these flux diagrams, or most of this stator is therefore occupied by these kind of flux lines, and similarly with this rotor. Now one thing is to be noticed is that these flux diagrams do not intersect in the way I've shown. This is just because my diagrams are bad, but typically flux diagrams do not intersect, right? When flux lines come close to each other, they produce a force and move away from each other. So flux lines do not intersect. This is just a drawing mistake, right? But what's important to understand is that if I consider the flux, right? If I can say that in this slot these flux lines are on the clockwise direction, then it is quite clear to understand that in this half of the circle, the flux lines are in one direction such that they are moving from the right to the left, right? You can see that. So for example, I can even draw a little line here, and I can say that these lines, in this half of the circle, the net flux is moving from the right to the left. So I'm not sure if I can add an arrow. I can't seem to find that entire function, so let me just draw it this way. Not the best, but it looks like an arrow, so it's okay. Yeah, it looks like an arrow, and I can do the same here as well. So for example, if we use the right hand thumb rule, we will find that these flux lines are in the counterclockwise direction. And therefore it's quite clear that in this half of the circle, the flux is also moving from the right to the left. So for example, let me choose this and let me draw it here. And let me just draw this here as well. So we have concluded that in both of these circles, the flux lines, as we see, is very clearly moving from the right to the left. And this is because we have chosen this convention of the current entering the page at the upper slot and leaving the page at the lower slot. Of course, this would be reversed if we reverse our convention, right? So if you're choosing another convention, just use right hand thumb rule and conclude on this on your own. But let us say that we have now considered that in these two halves, this is the net flux. With the net flux in both of these circles in the same direction, we can also now conclude that the total net flux produced by the stator will also be in the right to the left, right? This is something that we can conclude. So I could draw one single flux vector. I'm just going to try to figure out where the center is. Right, this is the center, and draw it from one end to the other end and put an arrow here as usual. Right, this is the net flux. This is the net stator flux which is produced by the entire stator coil winding, and this is perfectly understandable. For example, if you say that this is the coil produced, if this is a coil which is wound, you will find that the entire coil is going to produce a net effective flux which is moving from the right to the left. Because remember, again, it requires a little imagination, but if I were to flip this diagram and I were to look at it as a coil, we already know that the face of the coil in which the current flows in the counterclockwise direction is the north pole where it exits, and the face of the coil where the current flows in the clockwise direction becomes the south pole where the flux lines enter, right? This we already know. So therefore, let us now say that if this is the net stator flux, this net stator flux is now linking with the rotor. So now that we've come up with this, all these diagrams, I'm going to do something and I'm going to delete all these other lines, right? I'm going to delete all these other lines. You don't even need this, because otherwise it's impossible to make anything out in this diagram. Right? It's now much clearer. So let me also get rid of this and this. Okay, so we have now a stator, we have a rotor, we have the net stator flux, right? This net stator flux is now in this direction. Now the second thing which you need to know is that this stator flux is also an AC flux, because the current flowing through the stator is an AC current, right? If it's an AC current, it starts at 0, goes to a maximum, comes back to 0, goes to a negative maximum, goes back to 0, right? We know this. That's how a sine wave is, which means that this stator flux will also have the same pattern. It will be 0, it will reach a maximum, it will go back to 0, and then it will reverse direction. It will be from the left to the right. It will again go to a negative maximum, where again it is from the left to the right, but it has now maximum strength, and it will go back to 0, and so on and so forth. Right? So this stator flux is an AC flux which follows the same pattern as the AC current. So now that we've come to this conclusion, let us now look at what is happening with respect to the stator and the rotor. This stator flux is of course linking with the rotor. As you can see, it is linking with the rotor. Now the question here is the linkage exactly the same as always? Now for this, I'm going to delete this line. Oh, no, sorry. Should not have done that. I have to first ungroup the object. I have to ungroup because I grouped the entire thing. So I have to ungroup the object. Let me delete this line. Let me move this here to make it exactly the same as the stator. Right? So this rotor and the stator are now aligned, because we can see that the rotor axis is exactly aligned with the stator axis. Am I choosing the right one? No, I'm not. That's why. Unfortunately, I'm struggling even to draw a straight line. It's probably a glitch in the software though. Anyway, the idea here is, let me move, I can't move this. Yeah, this is definitely a glitch in the software. It's not letting me move. So anyway, this is the rotor axis and these are the rotor slots. Now, take a look at what's happening. The coil of the stator is wound exactly as the coil of the stator. And here I'm looking at a cross section, right? So the stator, rotor and rotor bars are actually cutting through this page, cutting through the laptop screen, right? We are assuming that they are current through the rotor is entering the page at the upper slot and leaving the page at the lower slot. But again, that doesn't matter because the rotor is not energized. We are only considering the stator. Now, if we do that, we see that the stator is passing through the rotor. This stator flux passing, or rather the stator flux is passing through the rotor. This stator flux passing through the rotor has maximum linkage with the rotor. The entire stator flux is being linked with the rotor. Of course, as always, there will be some leakage. We can never avoid that. But barring the leakage, all the stator flux is linking with the rotor. Now, again, I will select this entire rotor and let me group it again. And now what happens if I rotate it? So now I've rotated it in this direction because the rotor is rotated. If the rotor is rotated, now let's look at what's happening. The stator flux is the same, alright, because the stator doesn't move. The rotor has, however, moved. If the rotor has moved with respect to the stator, now what happens to the stator flux? This stator flux is now not linking with the rotor. There is almost zero linkage of the stator flux with the rotor. It's not passing through the rotor, right? It is just not passing because that's how the coil is. In reality, of course, this doesn't happen because the rotor windings are distributed, rotor bars are distributed around the circumference. But for now, for our purpose of understanding, we can see that the stator flux is now not linking the rotor at all. There is zero linkage. So, in this position, stator flux is maximum, or rather the linkage of the stator flux with the rotor is maximum. In this position, 90 degrees apart, the linkage of the stator flux with the rotor is zero. And we can keep rotating also, right? So which means that here, the linkage of the stator flux is back to maximum, and once again, it is back to minimum. So you can see here that there is some kind of a sinusoid which is happening. Now, let me ungroup it again. And let me give you the general case of what happens if this was the state. These were the rotor slots, right? If these were the rotor slots. Now, if these were the rotor slots, let me draw an axis. If these were the rotor slots and this is the axis, now you see that the linkage of the stator flux with the rotor is now between 0 and maximum. Alright, between 0 and maximum. Why? Because the entire stator flux cannot be, when is it maximum? When the stator flux is passing exactly 90 degrees in 90 degrees to the rotor axis. That's not the case here. There is an angle. That angle is not 0 degrees, the angle is not 90 degrees. The angle is some angle between 0 and 90. So this particular case, this general case that we've considered is a case where the stator flux is now having, you can say, a projection of the stator flux with respect to the rotor axis is now the flux which is linking the rotor. right? But most important, what is important from this entire conclusion was that as the rotor rotates, the stator flux which links with the rotor is now changing. And if it changes, then in that case, we can conclude from our Excel sheet that this MSR is dependent on the rotor position angle. Alright, it is dependent on the rotor position angle. At some positions, the stator flux has maximum linkage with the rotor. At some positions, the stator flux has minimal linkage with the rotor, almost zero. Right? So, we can now go back here and say that for this general case, what can we say? How can we formulate the linkage of the stator flux with the rotor? Is there a way in which we can do this? And the answer is yes. It's pretty obvious. It is from trigonometry. All we have to do is consider this orthogonal projection of the stator with the rotor. That is, we find out that in this stator flux, what component of the stator flux is now passing through this rotor in 90 degrees to the rotor axis. This is what we need to find out. We'll do that in the next lecture. This lecture has already gotten pretty long. But before we go, let me write this little conclusion, and we can say that mutual inductance between the stator and the rotor is dependent on theta m. And this is of course understandable, because otherwise, if none of the parameters were dependent on the rotor position angle, this wouldn't really be a mechanical system. Something has to be dependent on the rotor position angle. And in the case of a squirrel cage motor, the only thing which is dependent on the rotor position angle is the mutual inductance. Right? So, in the next lecture, we will try to create a formula in which we can determine how this mutual inductance is a function of the rotor position angle. This is what we need to find out. So, as before, if you have any doubts, please do either post in the comments or send me a message on social media or send me an email, whichever is your preference. Otherwise, I will see you next week, where we will continue with trying to figure out how the mutual inductance depends on the rotor position angle. Thank you so much for listening, and see you soon. Goodbye for now.